All right, so working on an achieved question about resonance, and you're given this protonated guanidine, and I went ahead and labeled N1, 2, and 3, even though these are all very similar, but the question asks for us to have them be differentiated, so 1, 2, 3, and the numbering doesn't matter, just that they're different. And it asks for two major structures and a minor one. So let's try to do maybe the minor one first. Thinking about resonance, we know we only need to move p orbital electrons in pi bonds. So I'm actually just going to break this pi bond and bring these two electrons to that nitrogen and see what results here. Okay, so I've redrawn this. I showed the pi bond breaking between N1 and this carbon. So the electrons went there, and that's represented by that lone pair, the two electrons in the pi bond, a lone pair. I need to make sure I balance my charge. So at this point, the charge is actually on the carbon there. Notice nothing happened with N2 or N3. They're just kind of there. But now if we look at this resonance form, resonance arrow, we've balanced our charge. No signal bonds have been broken. We only move electrons in p orbitals, lone pairs, or pi bonds. We end up with a carbocation here. And of course, the problem with the carbocation is that carbon doesn't have a full octet. So this would be a minor resonance contributor. It wouldn't be very likely because it has a carbocation. Now the other two major ones, and I'll draw one out, would be, let's say they take the lone pair from here, from nitrogen 3, go between the bond there, we make a pi bond there. So what's that going to end up with? All right, so what happened here? Lone pair came here, formed a pi bond. Got to make sure I balance my charge. So now who has the plus charge? It's actually going to be nitrogen 3. And then you could do a final resonance form. You could just redraw this if you wanted to. You could redraw this. Or you could take this and move those two electrons from 2 to form the pi bond. And then those electrons go to 3. And hopefully at this point you'll see what's going on. Nitrogen 3 got the electrons. We've balanced our charge. Nitrogen 1, 2, and 3. Formed the pi bond here. Those lone pairs broke that pi bond. There, those lone pairs right there. Major contributor, because everything has a full octet. The octet rule, again, is becoming important. Nomenclature question. So we have a structure like this, just has carbons and hydrogens. We need to find the longest parent chain. So that's the longest connectivity any which way. So we'll see 1, 2, 3, 4, 5, 6. Or we go 1, 2, 3, 4, 5, 6. Let's take this one. We could have done it the other way, maybe. Let's do it this way, though. So that's going to be a hexane. That's our parent chain hex because of carbons. Because of 6 carbons. We can either number this way, from left to right, 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. And we're going to number it so we want the lowest number of substituents possible. But before we do that, we should recognize what are our substituents. We have a dimethyl, and we have an ethyl. So we have the lowest number of carbons would be for the if we numbered it this way. So our dimethyl is a 2, 2. They're both on the same carbon. And this is ethyl's on 3. Now we got to do alphabetizing. So M and E, we don't include di, tri, or tetra when we do alphabetizing. E is before M, so it should be 3 ethyl, 2, 2, dimethyl, hexane. So this one's an interesting one because it gives you an incorrect name, and we wanted to draw out what this says and then actually give it a proper name. So it says heptane, so heptane means 7 carbons. 1, 2, 3, 4, 5, 6, 7. And it's saying 2 ethyl. And there's a 2, 4, 6 trimethyl. And they're telling us this name is incorrect. So possibly the longest parent chain is not being identified here. So let's see if we can find it. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. There it is. 8 is the longest parent chain. So that means it's an octane. What are our substituents here? We have, looks like we have tetramethyl. There's 4 methyls off this chain. All right, so there's 1, 2, 3, 4. We want the lowest numbers possible. So if we number this direction, we could go 1, 2. If we number here, we go 1, 2, 3. Well, 2 is less than 3, so we're actually going to number it that direction this time. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So it's 2, 4, 6, 6 tetramethyl octane. So you want the lowest number possible. The first number should be the lowest number possible. So that's the way this one would work. All right. So this is taking a expanded molecule. It's called isooctane. It doesn't matter what it's called, but we need to expand it out. So we need to number these carbons, or ways to take this empirical formula and make it into a line bond structure. So one of the things I would do would identify each carbon, or at least the carbons in the chain. And this doesn't have to do with the name, but 1, 2, and 3. So carbon 1 right here is bonded to what? What is carbon 1 bonded to? It's bonded to carbon 2. So this is carbon 1, carbon 2, which is bonded to 2 H's. And carbon 3 is bonded to 1 H. So what else is carbon 1 bonded to? So these parentheses and 3 means there's 3 CH3s bonded to carbon 3. Don't forget, how many bonds does carbon 1 have? It wants to have 4 bonds. So it's just a shorthand way to draw this. Carbon 2 already has 4 bonds. Carbon 3 is also bonded to CH3s, but 2 of them, hence the parentheses there, that is drawn. And they do ask for all of the hydrogens in the first version, and then in the second version, they just ask with no hydrogens. So what would that look like? So again, there's carbon 1, 2. Double check our work. Carbon 1 is bonded to 3 CH3s and has no hydrogens on it. Carbon 1. Carbon 2 had 2 hydrogens. They're there. Bonded to 1 and 3. All right, what was 3 bonded to? Bonded to 2. Bonded to 2. And H and 2 CH3s, and they're there. So it's the second part there as well.